Just get started. Welcome to CS3510. What was the number 16? Right, 16A. The power of randomness. This is an introduction, a gentle introduction into randomized algorithms. Randomized algorithms, again, we're in the post-NP unit. It's just a hodgepodge of a random stuff. Last time we talked about LP. We talked about the duality theorem. Today we're talking about randomized algorithms, at least in brief. So first off, it appears like at almost a philosophical level, what would randomness ever do for you? It seems like nothing. But it turns out that it can help a lot of times in situations that maybe making the right decision is really hard. You can make a decision and just kind of like live with it, right? So I'll give you an example. One time I was driving, and I forgot which foot goes on which pedal for which the brake, and then there's the gas, right? So there's two situations, and I'm pulling up to the light, okay? Two things can happen. One, algorithm one, okay? I can Google or ChatGPT or whatever, which pedal is brake. Or maybe I look in the manual, or, you know. Either way, this is I don't have time to do this. I don't have time to remember which pedal, you know, there's like milliseconds between me and the car in front of me. The algorithm two is just guess. One of the pedals is going to be the gas. One of them is going to be acceleration. It's 50-50. So what's the difference between these two? This one has 100% chance of working. But it takes too long, right? This one only has a 50% chance of working. But takes how long? We could say like O of 1, right? So if you're willing to tolerate a bit of error in your answer, you can speed up a lot about algorithms, right? If you're willing to say, you know, I only want the answer some percentage of the time correctly. Hopefully that'd be more than 50%. Maybe it would be like 99% of the time. If you're willing to accept the answers only right 99% of the time, then it can be the case that you can speed up algorithms. Now that seems contrary to the way we use algorithms. A computer and an algorithm, highly structured objects. How could they possibly be improved by randomness? They are improved by randomness at the cost of accuracy for all of them, right? Especially a domain that cares about this a lot, maybe, for example, packet switching. You have to route things in a certain way. You don't have time to say, okay, this is the optimal way, I'm just going to send things here. You can just guess and just say, okay, these things are probably going to go there, let's just kind of figure it out. And that speeds things up at the cost of accuracy, but it's fine. So people kind of live with it, right? You have to, if you do design randomized algorithms, you kind of have to tolerate a little bit of error, right? So every perfect randomized algorithm can be de-randomized. If a randomized algorithm is perfect, then you really don't need the randomness. You can just like do it without the randomness, right? What's the proof for this? Suppose you have a perfect randomized algorithm A. So A always gives the right answer, right? No matter what the randomness is, it's always going to give you the right answer. How can we de-randomize A? So a randomized algorithm, as we will see, we will allow it to be error prone. It'll give the right answer, let's say, only 99% of the time. For example, let's say you're looking for a SAT solver that's randomized. It gives a satisfying assignment, it gives 99% of the time, or a clique 99% of the time, and 1% of the time it gives something that's like not a clique. If you allow it to make error, you must allow randomized algorithms to make error, is what we're proving here. Because if you have a perfect randomized algorithm, I claim it can be de-randomized.
Can we we just run the algorithm once, get the right answer, go inside and see exactly what it did, and then instead of having random elements, we just do exactly what it did.
Basically, that's kind of like the idea I'm looking for. Control F, math.random. You don't know what Control S? It's an iPad kid here. Okay. Control F math.random for 0, 0, 0, 0, right? Replace the random number generator that it uses. Either true randomness, pseudo randomness, doesn't matter. Whatever decision it made under randomness, replace all of those with 0, 0, 0, 0, right? With some algorithm that it's basically the same API for a random number generator, but anytime it asks for a random bit, it's always going to give the same bit, not a random bit, right? So this is a de-randomized algorithm. So I mean that's just a normal algorithm, QED, right? You have to allow randomized algorithms to make a little bit of error. There are two kinds of classifications of randomized algorithms, maybe more, and they kind of fit into these two categories: Monte Carlo. Monte Carlo algorithm, Monte Carlo methods, probably the most popular, the most important one, in the sense that an efficient Monte Carlo algorithm always stops, hopefully in polytime, and it gives the right answer like 99% of the time. By the way, the error percentage of a randomized algorithm is not that important. Let's say you have a randomized algorithm that only outputs the right answer like 51% of the time. Why is that still okay?
More accurate than not.
Yeah. But why does the actual error percentage, like in a practical sense, not matter? Yeah.
If you need better accuracy, you can just run the algorithm multiple times, and whatever the most common answer is, you take that.
Precisely. Amplification.
Whatever level of precision you need.
Exactly. Amplification, a lot of randomized algorithms can be amplified in the sense like as long as the error is above 50%, even negligibly so, run the algorithm 10,000 times, take the majority vote. With high probability, that's going to be the right answer. If you know it gives the right answer 51% of the time, run it 10,000 times, 51% of those ought to be the right answer, 49 ought to be the wrong answer. You think that's going to give you the right answer, right? So in some sense, the error percentage, as long as it's not 50-50, can be amplified, so that's good enough, right? A Las Vegas algorithm, in contrast, eventually is expected to give right answer. And is always right, if it does. In general, by the way, a Las Vegas style algorithm does not need to stop. It's totally feasible for a Las Vegas algorithm to get stuck in an infinite loop and have an expected runtime. Like you can expect it to stop in polynomial time. But there is a situation where it never stops. It's stuck in an infinite loop. The same way, let's play a game. I say flip a coin, and you stop flipping the coin whenever you get a heads. There is a imperceptibly small likelihood, but never zero chance that you have to flip the coin forever. So sometimes Las Vegas algorithms don't have to halt. Classic example of a Las Vegas algorithm, and we'll spend more today on Monte Carlo than Las Vegas, but is BOGO sort. Has anyone heard of BOGO sort? Yeah, good. So on input 1 to n, we seek to sort this array. Okay. Here's how it works. Randomize A. If sorted, stop. Okay. So take the array, randomize it. If it's sorted, return that. How do you determine if an array is sorted? You can do a linear time scan. And if it's not sorted, re-randomize it. Over and over, eventually, will this guarantee that you output a sorted array? No. There's a chance that every time you randomly sort it, you go through every possible permutation except the one that happens to be the array sorted. The same way you can flip a coin and then there's a small probability, but never zero, that you never get heads ever again, right? It's the same way that this is not guaranteed to stop, but it's expected to stop. If you roll a dice, how many times do you need to roll a die to be expected that you'll get a 6? Not guaranteed, but expected. At 6, right? For the same reason, this is expected to eventually terminate, but it's not guaranteed, right? Questions on Las Vegas, BOGO sort versus Monte Carlo? Okay. So let's talk about an actual randomized algorithm. The first randomized algorithm was quicksort, really. And then of course there's de-randomized versions of quicksort where you make that, the pivot is chosen randomly to have an expected runtime, an average case runtime faster than the worst case. That wasn't really well understood until much later. But one of the first randomized algorithms was for primality testing. With primality testing, you want to give an n, is given n, does n have a factor which is between a factor f such that f divides into n, right? Let's say I ask you naively for this. Give me an algorithm for factorization, a deterministic one, let's say. Not factorization, excuse me, primality testing. I give you a number, and I want you to tell me if it's prime. Primality testing. Give me a deterministic algorithm, anyone.
Divided by every number up to that number.
Up to that number? So you know something about f. F must exceed 2, and it must be less than or equal to what? It can be smaller than n. In fact, you can search something less. Does anyone know this? We did this in 2050. I don't know if anyone remembers. Yeah?
Yeah, you only have to search up the square root of n.
Correct.
Because any factor that's larger than square root of n must have a pair that's be paired with one that multiply with a factor less than square root n to give n.
Let's prove it real quick. If n can be factored, then a is less than or equal to square root of n, or b is less than or equal to square root of n. Instead, we could prove the contrapositive. If both a is greater than the square root of n, and b is greater than the square root of n, then n does not equal ab. This is the contrapositive statement, right? What's the proof? A times b is, this should be strictly greater than, sorry. If we consider a times b, we know that a is greater than the square root of n, right? So a times b is greater than the square root of n times b, right? But that's greater than the square root of n times the square root of n, which is equal to n. So we know then that ab must exceed the square root of n. So that means ab does not equal n. Right? If both of its factors are greater than the square root, then those were never factors of the number at all, right? So we know that the number, if the factor exists, it must be less than its square root. But again, we measure the runtime, especially in number theory of algorithms, as a function of the bits it takes. So if n is k bits, then n is approximately 2 to the k, right? At most k bits. So square root of n is square root of 2 to the k, which is 2 to the k over 2, which is 2 to the o of k, right? So that's basically, if you check all the factors up to square root of n, there's still exponentially many of them. So this algorithm takes, maybe not a nice constant there, good for it, but exponential time in the number of bits of k. So this is still exponential time. So maybe not the best algorithm for factoring for searching. For primality testing, the best algorithm is definitely not searching, okay? Does anyone have another suggestion for finding, deterministically at least, the primality testing of an integer? Yeah. Yes, the C of Aristophanes or whatever his name is. Basically, you just, you know that half the numbers in here are going to be even, right? So don't ignore those. Half of those are going to be, another third of them are going to be divisible by 3. And a fifth of them are going to be divisible by 5, and so on. So just skip all those, and then eventually you'll find the right number. Turns out that actually takes too long as well. I don't want to analyze the runtime of that because this little skipping thing is difficult. Because 6, for example, is divisible by both 2 and 3. It's fine. That can skip around and find some things. So primality testing is not a naive problem, basically, because we can't think of one off the top of our heads. Anyone remember Fermat's little theorem? We all remember Fermat's little theorem, right?
What theorem?
Little theorem, not the last one. Yes.
No.
Yeah, you should know this.
Maybe I just don't know the name.
It's a problem about prime numbers and residue.
Oh,
If P prime and A is less than P, but greater than or equal to 1, then what must be true? This is a trivia question. It's not important. I don't know. I'm expecting anyone to get this, but I only know this because I teach only 50, so I have to know this. I'll just tell you. A to the P minus 1 is congruent to 1 mod P. Okay? The proof of such a theorem involves a little bit of group theory and bijections. I don't know if you remember this. You take a number, you exponent to P minus 1, you get 1, right? The reason this is true is basically because mod P, there's only P numbers mod P, right? So eventually, if you keep taking exponents, you must cycle back in some sense. But the proof involves a bijection. It's not terribly complicated. It's beyond us. But we can in fact use this for primality testing. If A to the n minus 1 is congruent to 1 mod n, that implies n is probably prime. Yeah, probably. It's not an if and only if that P is prime. If P is prime, this is true. It's not necessarily phrased to you as an if and only if that if this is true, then P must be prime. But that's okay. Because if a number satisfies that, it's probably prime. We'll elucidate that in a second. But this is called the Rabin-Miller test. Let's see if I remember. A takes on math.random, a 2 to n minus 2. If A to the n minus 1 is congruent to 1 mod n, return true. Okay? That's relatively efficient, right? I mean, there's some modular arithmetic. We know modular exponentiation is efficient. Modular arithmetic is all math.random is efficient. Two problems. First off, is this algorithm perfect? Yeah, so are there numbers that pass the Rabin-Miller test yet are not primes? Open-ended question. It turns out there are. These are called Carmichael numbers. There are not that many of them. The Carmichael numbers, there's 7 of them less than 10,000. In the first 10,000, how should I say it? 7. So in the first 10,000 numbers, only 7 of them are Carmichael numbers. But they exist. You can know what the Carmichael numbers are. In fact, the definition of a Carmichael number is a non-prime such that A to the n minus 1 is going with the 1 mod n. Okay? So the algorithm isn't perfect, but that's okay. What you can do is just run it a few, like 30 times or whatever, and then be like, okay, well, it's probably prime. You have high confidence that it's prime, but maybe it's not perfect. Turns out that if you amplify the accuracy to several 9s, I mean, that might as well be perfect. Except only in the mathematical sense it's not perfect. But in a totally engineering practical sense, all random number generators and primality testing in libraries are basically randomized, extensions of this as a randomized algorithm, right? Run it 30,000 times. If you're so confident, you can be more confident at the output of a number is prime than you could be in the, like, gravity is a correct theory or something, right? So put your Bayesian priors in order, it's fine, it's prime. Second, can this be de-randomized? Where's the randomness actually important here? Yeah, and is that important? This is an open-ended question.
well,
Subtly. And that's kind of the moral of today of randomized algorithms. Is like, what does the randomness actually do here? I don't get it, you know? Turns out no. It's like Rabin-Miller can be de-randomized if and only if the Riemann hypothesis or something like this, right? So probably not. Essentially, it's hard to de-randomize Rabin-Miller for this reason. So basically what happened is, like, in the 70s, people came out with this randomized algorithm and were like, oh my god, this actually works, and that's very scary because computation, highly structured, randomness, the opposite of that. How is it possible that randomness can speed up computation? the study of randomness in computation is now one that we've studied extensively, and it's still a very active and open area of research. What was inspired by this very interesting thing was it's like it's not really, it's still kind of mysterious about like why that works and so on, right? We did not have a deterministic primality testing algorithm. We've known about prime numbers for millennia. We've known about properties of prime numbers. We know about GCD. These are results going back to Euclid, right? And even further. But we didn't really have, we had efficient algorithms for multiplication and addition. Divide and conquer algorithms span thousands of years. We knew how to do all those efficiently, except primality testing. And for thousands of years, we had no idea how to do primality testing until 2004. 3 guys, AKS, I forgot, Agarwal, Saxena, something. Basically 2 undergrads and a professor at a school in India came up with a deterministic algorithm for primality testing in 2004. And the way they did it is they took a different, worse randomized algorithm that was something like n to the 4th, and were able to apply modern de-randomization techniques to it to get the right answer. But it took, this is from 1971, this is from 2004. Something like this, right? So it took several millennia or whatever for us to figure out really how to do primality testing deterministically. So only in 2004 did we realize that the prime numbers are in P. Even today, this algorithm is bad, so nobody uses it. But it's an interesting theoretical result. Rabbit Miller and its variants are still heavily used in every number theory library. Primality testing is done that way. Questions on primality testing, randomized algorithm for it? Kind of open-ended, right? Okay, let's consider another problem that's of significant scientific importance. How do you compute digits of pi? Everyone, some people understood pi to be irrational in a modern sense, but did not, they only understood to be, ancient civilizations knew approximations of pi. I think like 33 over 4, something like this. That doesn't sound right at all. 21 over what? What was it? 22 over 7, right? Yeah, that's the like Babylonian one. There's an Egyptian one that's like 286 over something, I forget, right? But basically people had some rational approximations of pi and said, okay, this thing's really interesting. And then eventually in like the 18th century, people proved it was actually irrational. Very difficult thing to prove. But let's suppose in an engineering context you want several decimals of pi. You only need a few decimals to have really perfect accuracy, but like let's say you want these decimals. What's one strategy to compute pi? Does anyone know algorithms for computing pi? Yeah? We'll do that one later, but for now let's do the deterministic one. Basic calculus. Tangent of pi over 4 is what? 1, okay. So what is pi equal to then? Okay, so if you can compute the tangent inverse function, you can compute pi. Okay, how do you compute a tangent inverse function?
You need like algorithms and stuff.
Yeah, that's one way to do it. There's another way. Taylor series. There's the Taylor series for tangent inverse of 4. Tangent inverse of 1. I hope I don't get the signs wrong. 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus, let me just double check I got the alternation correct. Yeah, that sounds right. Okay, so if you compute such a series, the series ought to give you accuracy to the number of terms that you get, right? So this is a numerical approximation of pi. So what you have to do in your calculator is you repeatedly add and subtract these fractions, and that's going to give you a decimal representation of pi, right? And in fact, pi, of course, can maybe like it's prime to have a Monte Carlo approximation for it because there is no way to get a complete answer. Pi is infinite, so like of course it's never going to stop. So it's okay if a Monte Carlo algorithm gives you something that's close to pi because it's fine. Let's say you only want 30 digits anyway. Don't expect the full thing. We can actually determine pi by just guessing. So suppose pi is a very informative constant. It shows up all the time in circles. It's So what we could do is just get a circle and then use the circle to find pi, right? So pretend that's a square and pretend that's a circle. What's the area of a circle? Pi r squared. So if we have and what's the area of the square?
4r squared.
Yeah. Right? Yeah, we'll do 4r squared. Okay? So if we can get the area of a circle, we can obviously compute pi just by taking the division and multiplying by 4, right? So if we could somehow figure out how to compute the area of a circle, then we could use that to compute pi. That's actually the opposite of how you would think, because usually you need pi to compute the area of a circle. But if you somehow can get the area of a circle, then you can use that to compute pi. Now, how are we going to get the area of a circle but without pi? How can we use the area of a circle to get pi?
You put grid lines, boxes, and then count them.
Ah, see, that's an algorithmic approach. Let's say you're doing something like this. Is this what you're saying?
Yeah.
And then you count areas of those little things? Okay, I have a better answer for you. Power of randomness, just guess. What we're going to do is just get, instead of actually manually counting any boxes or anything, we're just going to say, like, we know when it's in the circle. We know when a point is in the circle. When is a point in the circle?
When the component's square to less than r squared.
Let's say the radius is 1. What is true?
Then the component's square to less than or equal to 1.
Yeah, x squared plus y squared is less than or equal to, let's say, 1. Right? So we know when a point is in the circle. We also know when a point is not in the circle because it's not in the circle when it's greater than 1, right? So in fact, all we can do is just randomly guess points and then just count the ones that are in the circle. Okay? Suppose we let this be a unit square of 0, 0 to 1, 1. And let this line denote when a point is less than or equal x squared plus y squared is less than or equal to 1, and this is x squared plus y squared exceeds 1. Okay? Let's throw darts at the whole thing. Just throw darts. Just randomly start throwing darts, and let a dart be consistent of a pair of points x, y. Both two real numbers. Approximated maybe, but fine. 32 bits, whatever. FIPS, IEEE 78, whatever. Right? Throw the darts there. We want to compute what is the probability a dart hits the region. Let this be the good region. I'm asking what is the probability a dart hits the region?
It's just the area of the
Exactly. If it's proportional, it ought to be the area. What is the area of this circular region?
The radius is 1, remember?
Yeah, but let's just say r squared so I can cancel them out right now. Which is, okay? So in fact, the probability the dart hits the region is pi over 4. That we can use that to find pi if we can find the probability that we hit the region. But how can we find that? All we need to do is this also ends up being equal to the number of hits divided by the total darts. Well, a hit means that x comma y is x squared plus y squared is less than or equal to 1, right? If a dart hits the region, you say plus plus, and to totals you say plus plus, and if it doesn't hit the region, then you only say totals plus plus, right? I wrote some Python scripts. Let me show you them now. Let's do that one, and then let's do Okay, can we all see that? Okay. Let's see. Is that too small?
It's a little bit too small. Can you?
Oops. So this is the Taylor series problem. It takes as input n, and then it just adds or subtracts the odd fractions in the numerator and denominator. I have a hard-coded value of pi there, and it computes the error estimate. So let's just see how accurate this is up to certain terms. Give me an n. Let's do 100. Let's do 10 first. Okay, so with 10 fractions, we are up to like 3% error. That's not bad. Let's do 100. We are up to 0.3% error. Zero 0.03% error. But you notice the error, I mean, like the last two digits of pi are really small. So getting those with fractions is going to be really hard if you think about it. The fractions don't get smaller faster than the decimal does, because this is 10 times that one, right? This decimal is 10 times smaller than that one. But the fractions are going to be alternating. So it takes actually a lot of fractions to get the next decimal, it turns out. So you need more terms. The error, this is hard to like formalize, but the number of terms is not proportional to the error. To get the error small, you need way more terms than necessary, right? Let's just do like 10,000. Okay, e to the minus 5, 3.1414, okay. That's not that good. Let's just do a lot. 10,000, 100,000, a million. Okay, you can see it took a second there. So the longer, if you want a more accurate representation of pi, of course, it's going to take longer. Okay, that took a few seconds to calculate, but it works. Fine. What about the Monte Carlo method? Nope. Is this the one? Yes. So here we go. I generate n random points, separate independent x and y values, and then I say if x squared plus y squared is less than or equal to 1, hits plus plus, and then n is my total here. And then I just return the estimate as 4 times the hits divided by n, which is exactly the value we hope it to be. So if I do Python pi, and then let's do 100. That was pretty fast, but the error is really bad. We have 3.36. That's definitely not pi. Even for 100 points, that's not so good. What about 1,000? 3.2. That's also still not pi. That's not pi enough, right? Let's do 1,000. 10,000 points. Okay, 3.13. We can see this has less accuracy if there's points proportional to fractions. Of course, the fractions feel faster, right? If I do, let's just do a million. Took a second there, but we get worse error. Now the moral here, I was supposed to say like, wow, using randomized algorithm computing pi is actually faster using a randomized algorithm than using a deterministic one. But that's not true at all. But it's just a demonstration how you can do something randomized, not necessarily faster, but at all when there are deterministic methods for it. Let me show you what. So here is the same piece of code, except this time I have thrown it into, what's that called, matplotlib, right? So let's do, let's do 10 points, okay? So here are the 10 points that we have thrown there. Blue represents that it is less than or equal to x squared plus y squared is less than or equal to 1. And the red point, the single red point, is in the outer region. So now we don't really, this is obviously not going to be right. This is definitely not any kind of representation of pi because it's like 9 to 1. It said pi was 3.6. That's not very good. Let's try n is 100. Okay. Maybe a little better, but not really anything. I'm not sure what's going on over here, honestly. That sounds wrong, right? Maybe is that the edge? Okay. Let's try 1,000. So we can kind of see a line of demarcation begin to form with the more points that we add. Let's do 10,000. We will pretty clearly see when a point, we're not drawing any circle, there's no circle math. We took x squared plus y squared less than or equal to 1 and said color it blue, otherwise color it red. Yet we see the circle start to emerge. And as we zoom in, we see that there is no, how's it? We see that, again, there's nothing here except dots, right? Let's try even more. That got us pretty close to looking like a circle, but again, it still says only pi is 3.11, which is not right at all. Let's just go for a big number. 100,000? Let's do 1 million. So it generated the thing, now it's doing the matplotlib of 1 million points. By the way, when I got this job, they asked me if I wanted the highest end spec Dell XPS or the highest end spec MacBook thing, and I said, no thank you, I'm going to keep using my 13-year-old Chromebook. Because first off, so what is it? You got a new computer, first off you have to turn on the computer, you have to open the computer, you have to update the computer. I don't have time for any of this. So this computer, it's, and especially in the world of theory, this computer is 25 times slower than any modern phone or anything anyone uses, but that's just a constant. So all the algorithms are still big O of all the same things. It does take matplotlib to load for a second, but again, it loaded, right? Would 1 billion points have illustrated this point any better? No. So it's fine. There's so many points here, it's almost indistinguishable about, it obviously looks like a perfect circle, right? But again, if we zoom in, let's see. We see it is just, this guy is maybe 0.99 and that guy's 1.01, right? So, and let's see, given 1 million points, how accurate it was. 3.1416, which is, that's not very accurate at all. But either way, we see you can use Monte Carlo methods to estimate a Python program. Now, why do you care? Like, let's see, let's turn that off. So I'm saying this algorithm is worse. We see that the runtime is worse. By the way, both of these algorithms, kind of engineering domain, because it's difficult to analyze the runtime of either of them. But I claim that the Monte Carlo method algorithm, sure for this problem is not as good, but it is extendable in a way that the original algorithm for change in inverse is not. I'll give you an example. There was this problem in 2018 at the Mercer programming competition, which doesn't exist anymore, where you were basically, it was called the Fortnite problem, because you were asked, like, within a ring of whatever, what is the probability that the next ring you will be in the next ring? And it asked for 2 decimal places of basically you computing the intersection of 2 circles. What is the area for the intersection of 2 circles? So we all know the area, the formula for area of a circle. What is the formula for the intersection of 2 circles? So here's the formula, quote unquote. Would you agree that there's a point here, this is a center point, and then there's a radius 1 here, right? These are something like this. So you can compute this deterministically. Are you going to remember how to do it? Of course not. But here's what the formula is. To compute that area, first you take this sector. How can you find that sector? The pizza of the left half. Well, let's suppose it's a varying angle. It's somehow a function of the intersection. Yeah, so as a function of the area, what is this slice of pizza shape?
It's like a function of the radius and the degree of the angle.
Yeah, exactly. So in fact, whatever this angle is theta, it's like theta 360s of the area. Would you agree if this theta is 1/2, is 180 degrees, then the area of this is literally 1/2? The theta exactly proportions what this shape is. Would you agree? So if this is 1/4 of 360, then this is 1/4 of the circle, right? So it's just a little ratio of the actual area. So you could find that out, knowing the theta, okay? Let's say you're given input as R1, R2, 0.1, and 0.2. If you're given those two values and those x or y coordinates, you can compute this r1, and then you can compute this theta, you can compute this intersection, you can compute that, fine. Then you subtract off the area of this triangle, right? How can you find the area of a triangle like that?
You have to have some function of the radius that accounts for like it decreasing.
Yes, and it's not too hard to do that. There's a formula, for example, if 3 sides of the triangle, let's say you have another side here. If you have 3 sides, you can compute the area. I think it's Heron's formula. It's kind of this complicated square root of alternating something. If you have side angle side, maybe you could do something, I forget. There's a million ways to compute the area of a triangle, okay? Find one of them, find the area of that triangle, and subtract it. What is this minus this? Half the football, right? Similarly, you just do the opposite. Yeah. That's going to give you this half. So you add those two together, that's the area of the intersection. Fine. That's the way to do it deterministically. That works most of the time, but are you going to remember how to do that? No. But you can do it really easy with Monte Carlo algorithms. So again, if you don't know how to do it, you could just kind of guess, and it'll tell you how. So here's the algorithm I claim will work. First, find some bounding box, doesn't really matter. Estimate one through the areas. Okay? 2, throw darts. Okay? If it hits the area, increment a counter. If it hits, yeah, that's it. If it increments a counter, right? So now you have a set of darts in the region. Given a point cloud like this, you could find the area as a proportion of, I mean, that's it. It's the same trick. Just find, it's the area. The probability it hits it, assuming uniformly random darts, is the same. So that same ratio trick will work for this. What you do to check if it's in the intersection of 2 circles, you do an and if it's in this circle and in this circle. Fine. Now suppose you wanted to find something else about this shape. Let's say you wanted to find not the area, but maybe something more informative, maybe like perimeter or something, right? Just to emphasize what else you could do, you could, in fact, take the points that are in the intersection and then find the convex hull. Anyone know what the convex hull of a set of points is? A convex hull, sometimes I think people do this in 1332, but you have a set of points like this. The convex hull is a geometric algorithm that finds for you the exterior set of points of the set of the point cloud. In 2-dimensional space, it finds all external points for you, right? The algorithm uses a stack. It's called Graham scan. You basically search over the thing until you find the right thing like this. So either way, there's off-the-shelf convex hull algorithms. You could just Google convex hull algorithm and copy and paste whatever you find. So what you do is first Monte Carlo it, find the convex hull. Great, now you have a set of points for the exterior polygon. Then you take any polygon area counter. What is it? Polygon perimeter counter. Right? Compute that distance, then that distance, then that distance, then that distance, and that'll give you the perimeter. So Monte Carlo, you can also approximate the perimeter. That's pretty important, especially in cases where there's no other way to compute the perimeter, right? So there are situations where you literally cannot compute the perimeter, right? Consider an ellipse. Everyone know what an ellipse is? What's the formula for the area of an ellipse?
AB.
Yeah, it's like, instead of pi r squared, it's like pi AB. Right? In general, an ellipse, I have to write this one down. An ellipse can sometimes have a nice form, sometimes it doesn't. Here's the general form of an ellipse is ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. It's a generalization of a circle with a kind of a slanted, like a stretchedness to it, right? That's the general form of an ellipse. It's almost like a circle. We know that for a circle, what's the perimeter of a circle? The area of a circle is pi r squared, and the perimeter is what? What was it? Yeah, it's 2 pi r. The area of an ellipse is pi AB. Oh, sorry, I didn't mention. This is A, that's B. Okay? It's basically like the generalization. If you imagine A equals B, this is just pi r squared. What is the perimeter of an ellipse? That's actually a great conjecture, but no. That sounds like it would make the most sense. Perimeter ought to be additive, area ought to be multiplicative. That makes sense, but no.
Geometric mean.
How so?
Pi root AB.
That doesn't work either. Yeah?
No, I don't remember exactly, but I know there's like some whole infinite series shenanigans thing you have
Yeah,
to
so the
really hard.
exactly. So the answer is there is no formula. There is no formula for the perimeter of an ellipse. What you can do is take, using like, what was it, Green's theorem or whatever, you can do a line integral over that and try to figure out what that's going to give you. And that, you could do a Taylor series approximation of that, but that'll never give you a closed form, right? There are certain integrals that have no closed form, but you still may want to compute the area of. Another such one is e to the minus x squared dx. That's very important, right? This is like Gaussian stuff, but there's no closed form of this. You can never compute the integral of this, but using Monte Carlo methods, you can compute areas and perimeters and approximate areas and perimeters in ways that are really simple that have no mathematical way to do them at all. There is no, it's provable that there is no solution to this, except the Taylor series expansion, but that's it, right? So either way, this works in situations that a lot of just high-level math fails when you can just randomly guess a solution to a problem and just kind of like hope it'll work. The reason I'm mentioning ellipses is there's another problem you can do with an ellipsis. If you're given an ellipse of this form, you can use that equation still to determine if a point is within the interior of the ellipse for the same reason. You could determine if x squared plus y squared is less than or equal to 1, right? There was a problem, in fact, last fall, ICPC, of how do you, given an ellipse like this, determine a bounding box of the ellipse? How can you do that effectively? Bad answer is to figure out tangent points and then like maybe do a walk along the exterior of the function or something like this to find a max point and a min point. That's not very, let's not do that. How can you effectively find a bounding box for the, yeah?
Do we need to find the smallest possible bounding box, or can we just do any bounding box?
Oh, that's a great question. And it'll tolerate, the judge will tolerate a small amount of error, but you want the smallest bounding box.
Okay.
Let's say it has 1%, it allows 1% error.
What are you given? Are you given that?
You're given that, you're given A, B, C, D, E, F. Parameterization of the ellipse, yeah? Yeah.
I mean, is there a runtime limit? Because otherwise you could just trace to the top and find the highest point and like basically the extreme points of the ellipse and draw the box around that.
I guess two problems would be like how you can be given a lot of exotic ellipses, right? And equations of this form sometimes aren't even ellipses. They're like hyperbolas that are unbounded in some sense. But if you're promised that it's an ellipse and that it has a bounding box, give me an efficient way to estimate the bounding box. You're claiming you can find the highest point. How would you find the highest point?
Well, if it's a formula, then you can probably situate it in a graph sort of situation.
I mean, like, do you know how to implement that? Like, gun to your head right now, could you do that in Python? Could you figure out how to find the like Desmos find the max? Finding the maximum of an ellipse is not I think a simple thing, right? If it's nice and perfect like that, you can say, okay, I know where that point is. But when it's like this, or something more exotic, it's like the max point is not. I don't know how to find the max point that way. Could you describe your algorithm in more detail?
Well, the y value, the highest y value that satisfies the equation would be the highest point, right?
Okay. How do you find the highest y value that satisfies that equation?
I mean, that's why I asked if there was a
Or you
runtime
could-
limit, because you can just keep checking continuous values.
So how do you find a continuous value in a discrete sense?
Do calculus and maximize y with respect to x.
There's two variables here, and you can't rewrite this nicely as y equals f of x. That's the reason it's interesting, in fact, ellipses. No ellipse is a function for that reason. I'll ask again, how can you find a bounding box? Yeah.
I'm just going to throw a bunch of points within the ellipse, take the farthest one on each side.
That's it. That's the answer. This is a Monte Carlo lecture, right? It's a randomized algorithms lecture, okay? Take the ellipse, start throwing darts. You know, you have a simple check, an arithmetic check if they're in the interior, right? So,
Wait, so how do we,
I'm listening.
where are we throwing our darts?
Everywhere.
No, but like everywhere on the whole infinite plane?
Yeah, sure. Suppose the problem is parameterized in such a way that you know it's between something simple.
So we already have a bounding box, so we just get a smaller one?
Yeah.
So you know at least that those are.
I mean, you can suppose like the problem is given in a way that makes sense. If the constants are not bigger than 1 billion, then you know the bounding box to be 1 billion, right?
So if you have a bounding box, why can't you just binary search the heights of each one until you have?
That would work too. But how do you? Then there's some non-trivial questions there. How do you? And in fact, a non-trivial solution to this is binary search. How do you determine though, like bounding box lying too low, bounding box lying too high? How do you determine it's too low? You check that there's a point above it, but how do you determine that? The moral is basically it's really hard for a computer to do calculus. It either has to do it algebraically in the sense that the calculator literally manipulates things, or it does estimations using floating point values, which is itself a different kind of, there's different problems there, right? I don't think binary search is the worst idea though. But the spirit of the problem, especially in today's lecture, is Monte Carlo. You don't have to think about it. You can just guess, and because you have a method of verification, you just make sure it verifies, okay? You take the point here that'll determine the bounding box value is up to Monte Carlo, the point that satisfies two things. It's the highest, it's the point that satisfies the inequality, and also it's the point that has the largest y value of all the points. You are guaranteed that it's not some y value over here or something, but also a y, literally, you know what I'm saying, right? We get it. Similar here, this is the point with the smallest x value, the point with the largest x value, and then the point with the smallest y value. Those 4 points, max and mins, determine your bounding box. That's fine. Incredible in this is you don't even need to keep track of the number of points or anything like that to do Monte Carlo. You need at most 4 points. So you can repeatedly throw darts, and instead of keeping track of any integer for computing an area or something that we've done previously, you keep track of only the 4 points. If it's currently greater than your current maxes and your 2 maxes and your 2 mins, then you replace it. Otherwise, just keep trying. And as long as the autograder is willing to tolerate a bit of error, this will effectively work for most of the time, right? Okay, maybe any questions on this?
How many points do they have to throw?
So I'll tell you specifically for this problem, the area intersection problem. I went with 3 teams to Mercer, and one team actually did something like this with Simpson's rule. They were able to estimate something really terrible through a very complicated integration method. They were actually able to solve the problem. So they did do it with integration. The other team did Monte Carlo. They implemented it in Python. It did not pass the grader. It was too slow. They re-implemented it in C. They gave it to the autograder. It worked. So, and the only reason it worked is that the autograder only asked for 2 decimal places. If it asked for any more, this would have been insufficient. It said, just give us the area up to 2 decimal places. And that's like a hint, like, you probably want Monte Carlo for this. That'll pass the autograder. So I don't know how many points they have to do, but that's like a very practical something to figure out. Okay? All right, I'll give you one more algorithm. Suppose you want to find 2 coloring of a graph where at least e over 2 edges, half the edges, have opposite colored endpoints. So we know, of course, not every graph can be 2 colored, right? What is it? The triangle definitely can't be 2 colored, and so on. But we seek a two coloring of a graph where at least half the edges are colored. So consider this graph, maybe. Something like this, right? This graph, of course, is not two colorable in the absolute sense, but we can still find an approximate two coloring. Give me like maybe a greedy method to solve this problem.
I guess just start with a color and then all of its neighbors choose the other color.
Yeah, that would probably work, right? But there's some there's a lot of when you do it the right way, quote unquote. There's a lot of things in the way, like what if you chose a node adversarially so that this never happens, like something bad happens, right? For example, a wheel. Actually, no, that's a bad example. But there's some graphs you could choose, I'm certain, that would, maybe a clique. Let's do a clique.
Oh, that's a good example.
Blue, red,
They're all red.
then they're all red. So then those six, but that's one half. We'll call that one half. Yeah. Right? There's 4 here that are going to be good edges, and then these n minus 1 choose 2 are all going to be bad. So that's a bad example. So that's definitely going to not work on some inputs for certain choices, right? I claim there's a randomized algorithm that can solve this effectively. What is it? Okay, randomly assigned colors. What if you don't get a coloring? Yeah, okay, that's the answer. So this is in fact a Las Vegas algorithm that works half the time. We expect each edge, if you assign a random coloring, what is the probability an edge has the property? Yeah, so if each edge is colored independently, the two endpoints could either be red, 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 blue, blue, red, or blue, blue, right? So it could be one of these. So these happen 1/4, 1/4. This is 1/2. 1/2 of the time, an edge is going to be colored randomly. Good. Okay? So if you have a coloring, and with actually very high probability, a random coloring will satisfy this property. So if you find one that doesn't, just throw it over and try again. Because with high probability, a random coloring will satisfy this property. And if it doesn't, then you throw it over and you try again. If you just repeatedly randomly try to color a graph this way, with overwhelming probability, you'll have some coloring have half the edges with this property, right? Eventually, that must be the case. Why is that? There's a more general thing you could say about something like this, right? If you have any kind of distribution, and you randomly sample points from a distribution, what is the probability you get something above the mean? Yeah. So half the time, you're above that. If you flip a coin, half the time it's heads, right? If you generate a random number between 0 and 1, half the time it's above 1/2. So suppose you generate a random number between 0 and 1. Like a real number between 0 and 1. And let's suppose it's even uniform. So what is the probability that you get a number above 1/2? Yeah, half the time. So what's the probability if you generate 10 random numbers this way, one of them is above 1/2? I'll ask you the reverse problem. What is the probability you generate 10 random numbers and none of them are above 1/2?
1/2 to the
Yeah.
very low.
If in K trials, none above 1/2, the probability of this occurring is 1/2 to the 10. Because the first one is below 1/2, the second one is below 1/2, the third one is below 1/2. So the probability any of them are above 1/2 is 1 minus that. So as the number of trials increases, this becomes overwhelmingly likely to happen. The graph coloring thing is just kind of a rephrasing of the same property, even though the edges are technically not necessarily uniform. Right? Questions on randomized algorithms? Didn't do any runtime analysis, didn't do any probability calculation. That's fine though. We'll talk about something else when we come back from the break. Questions?